So last time we studied the sheaf of Keller differentials, and one more thing we will do now is how it, well, in a sense, helps to decide which equations define subvarieties. So let's prove the following proposition. We consider a smooth subvariety X and Y. So Y is also smooth. And let X be a point. And let us take the defining ideal. So Jx the ideal of functions vanishing on X. And now let locally around this point.
У Y принадлежит. Не у X, а у Y.
Yes. So we consider locally around this point. So we consider functions f1 and so on, fn in the localization of this ideal in the stock. Such that first of all, n is the codimension, and also the differentials are linearly independent. In the cotangent space at this point. Okay, then I claim that the ideal J is locally generated by those functions. Okay, around this point. And also, we have the following exact sequence. Goes to the sheaf of Keller differentials on Y restricted to X, goes to the sheaf of Keller differentials on X. So this is an exact sequence of sheaves, and at the level of corresponding vector bundles, we get the conormal vector bundle. It embeds into the cotangent vector bundle on Y restricted to X, and in the quotient you get the cotangent vector bundle of X itself. So this is called the conormal vector bundle. Okay, and in particular, the top exterior power of the cotangent bundle well, the Keller differential sheaf on Y restricted to X is isomorphic to the product of the top exterior power of this ideal modulate square tensor, the top exterior power of omega X. Okay, as we discussed in the end of the last lecture, and then this determinant is also denoted omega Y.
Это детерминант
The canonical line bundle, yes. Well, sorry, it's called the canonical line bundle.
А как определяется матрица или вот это омега Y? Это детерминант же мы берем от матрицы?
No. This if the rank of the cotangent bundle is say D, then when I write determinant omega Y, by definition, this is the top exterior power, namely D exterior power of this cotangent bundle. Okay, this is just definition, not notation. Okay, I mean it is really etymologically related with determinants of matrices. Namely, if you have a matrix which defines an endomorphism of say local endomorphism of this vector bundle, then it induces some local endomorphism of its top exterior power, right? But since top exterior power is an invertible line bundle, then its endomorphism locally is given by multiplication by a function, and this function is just the determinant of this matrix giving an endomorphism of the vector bundle we started with. Okay, so once again we get that the canonical line bundle of the ambient variety restricted to X is isomorphic to the canonical line bundle of X itself, tensor the top exterior power of the defining ideal modulo its squared. Okay, so this is an important formula, and I will prove this proposition in the next page, but here let's formulate a corollary. So in this corollary, this codimension n we had above is just one. So X is a smooth divisor in a smooth variety Y. Okay, and then this formula for the canonical line bundles is called, in this case, the adjunction formula. And it says that the canonical line bundle of the divisor is the canonical line bundle of the ambient variety, but you twisted by this divisor, sorry, X, this divisor X, and restricted to the divisor X itself. Okay. So when I write, maybe let me go here, omega Y of X, it's a line bundle, is omega Y tensor O Y of X. If you remember from the last year, each Cartier divisor, in particular a smooth divisor in a smooth variety, gives rise to a line bundle. So there's a line bundle of rational functions having a pole of degree at most 1 along this divisor. Okay. So this is a very important calculation. For example, if you apply it, well, maybe let's go to the next page. So we take y just the projective plane, and x an elliptic curve. And so there's a cubical curve. So in other words, a smooth cubic. Okay. So then we calculated in the end of last lecture, we calculated omega y. This was OP2 of negative what? Anybody remembers by any chance?
-3.
-3.
Right. Thank you. Right. Thank you. And on the other hand, y of e is what? Can anyone guess?
O of 3.
Right, it's O of 3 because e is a cubic, and it implies that the canonical line bundle of this elliptic curve is just trivial. And the form omega, well, I apologize for some notation clash. This omega, on the one hand, defines denotes a line bundle. On the other hand, it denotes a section of this line bundle. I'm sorry. Sorry about this. A form from the home assignment. Trivializes this canonical line bundle. That is, this form corresponds to the section 1, the global section 1 of the structure sheaf. Okay, and we know that the structure sheaf is the same as the canonical line bundle. Okay, so this was some comment about this proposition. So let's go back and have a look, have one more look at this proposition. So the key point was here. It says that we can find out when a collection of functions really does generate the defining idea. Okay, and it only says that the number of functions must be correct, namely equal to the codimension of our subvariety, and their differentials should be linearly independent in the cotangent fiber at this point. Okay, and that's it. And everything else follows from this immediately and formally. So this is what we really have to prove.
Владимирович, можно спросить?
Yes.
А почему омега y ограничение на x не совпадает с омега x? Это из-за того, что кольца
they're of different dimension. Yeah. For example, let x be a point. Then its cotangent bundle is just 0-dimensional. It's nothing, 0, right? Because a point has dimension 0, but the ambient variety was n-dimensional, and if you take the fiber of its cotangent bundle at this point, it's still n-dimensional vector space, right? So it's much bigger. Yeah, the rank of the cotangent bundle is equal to the dimension of your variety. But when you restrict, you just get the same dimensional vector bundle, just restricted to this subvariety. Okay.
Да, и получается, но x под множество y, значит, когда мы омега y ограничим на x, мы получаем то же самое, что омега x?
No, we just get the restriction to x. It has the same rank as the initial cotangent bundle to y. For example, if you take its fiber at any point, it has a rank n. Well, the rank dimension of y. Welcome. Okay, so let's go and prove this equality. Okay, so let's consider some intermediate ring A. By definition, this is the quotient of the structure sheaf of y modulo the ideal generated by these functions, f1 and so on, fn. Okay, so it's a sheaf of rings. In a neighborhood of x, where all f1 and so on, fn are defined. So recall that those f1 and so on, fn are local functions. They're defined on some open neighborhoods of this point small x. We take the intersection of those neighborhoods where all the functions are defined. Okay, so then we, because all those f1 and fn, they do vanish on x, we certainly have a surjection from A to OX, and we want to check that it is an isomorphism locally around x, the small point. Okay, and now consider the associated graded. G of A, just the sum over all positive integers, the maximal ideal of this local ring of x times A modulo the next power, like, okay, and then this is generated by the image of the cotangent fiber at this point, modulo the differentials of these functions. Okay. And this is just a vector space of dimension. Oh, sorry, it was not x here. I'm sorry, but y. So the functions are on the big ambient variety y. The dimension is the dimension of y minus n. This is just dimension of x. Okay, but on the other hand, we know that if we apply this associated graded procedure to the ring of functions on x, as we did last time, so recall we considered maybe even a week ago, the associated graded G of local ring like this. Yeah, the spectrum of this thing was the Zariski tangent code, right? Modulo taking quotient model nilpotent. But anyway, this is the polynomial ring in dim x variables, right? Because x was supposed to be smooth, right? So the Zariski tangent cone is just a vector space, and this associated gradient is just a polynomial ring. And also the we had this surjection from A to OX, right? So at the level of associated gradient, it's also a surjection. We had the surjection from A to OX. Okay. So it means that this necessarily must be an isomorphism. Right, since the dimension, this is just a polynomial algebra. Oh, sorry, maybe I should note the coordinates t1 and so on, t dimension of x. And this has dimension the same dimension. So such a surjection necessarily must be an isomorphism. Okay, because it gives rise to a subvariety of the affine space that has the same dimension, so it must be again the polynomial algebra. Okay, so we're almost done. We know we have this surjection, and we know that at the level of associated graded, the induced map is an isomorphism. And then just as we proved last Thursday, I think, the intersection of all maximal ideals powers in the local ring OX is 0, and similarly, the intersection of all powers of maximal ideal applied to A is also 0. Just the same argument proves this, but then it implies that at the level of non-graded rings, we also have an isomorphism. Maybe locally around X. Right, because just somehow by induction, if you have this surjection from A to OX, yeah, suppose it has a kernel. Now this kernel that does live in some power of maximal ideal, but that does not live in the next power, right? Because the intersection of all powers is 0. There must be some maximal power where it doesn't, well, maximal number where it does not live, but in the previous one it does live, and then it gives rise to a kernel on the associated gradient. But we know that there is no such kernel. We proved this here. Okay, so there we are. Fine. the proposition is proved. And the adjunction formula follows, for example. So now let's move to another topic, namely the morphisms of varieties and dimensions of fibers. And essentially, what I am going to recall now what was done in home exercises last semester, but maybe not everybody solved them or somebody forgot them. So let me go over it once again. Oops. Okay, so we'll have a morphism f from x to y, and we will consider its image, but its image can be somewhat bad. Yeah, maybe we already discussed this half a year ago. Let's discuss once again. So the image can be not open, certainly not necessarily closed. That's no question, but it can be not even locally closed. Not locally closed. That's what I call bad. And probably somebody remembers the basic example of this unpleasant behavior. Anybody remembers? No?
For example, A2 with functions x,
right.
y, and y.
All right, absolutely. Thank you. So it's called a fine blow-up. From A2 to A2. I mean, you can consider the standard blow-up. Then it will be some proper morphism, but in this total space of the blow-up, you will have it will be covered by a few affine charts, and this is just one of them. So as Alexander says, the map in coordinates x to y is goes to x and xy. Okay, and then what is the image? F of A2 is essentially A2, but without what? So you see, you if x is 0, then xy is necessarily 0 also, right? You vertical axis, right? But you can go to the origin. Okay, so there's the picture. There is no vertical axis, but there is the origin. Okay, so the image is something strange. It's not locally closed. It's called constructible. I mean, it's a finite union of locally closed subvarieties. Okay, and indeed, this is a theorem by Chevalier, Claude Chevalier. That the image, well, this f of x is always constructible in Y. Okay, and we're going to prove this theorem, but after some preparations, or it will be a corollary of the next proposition. So it says that the image f of x in Y contains an open dense subset U. So it'll be open dense in the closure of this image. Okay, so as we just saw, the image itself is something bad. It's not an algebraic variety, for example. It's a subset, but just a constructible subset. But if you take its closure, then certainly there's a subvariety. In this example of affine blow-up, the closure will be the whole of affine plane. And now I say that the image contains something which is open in the closure of this image. Okay, and it's not just this, but over this open subset, the dimension of the fiber, maybe I should say small u, is locally constant over u. Okay, and if this image closure is irreducible, for example, if x itself is irreducible, then the dimension of this fiber is just the so to say codimension, the relative dimension. So dimension of x minus the dimension of its image for any point in this open subset. Okay, so for the proof, we may assume it's a local claim, so we may assume that Y is the closure of the image because we're interested in nothing else. We may assume that it's irreducible. Affine, and X also irreducible and affine. I mean, everything is clear, maybe, except for irreducibility of X. But then, if you prove the above proposition claim for each irreducible component of X separately, then it follows for the whole of X. Okay, so now let's prove the following key lemma. This key lemma is essentially a Minota lemma. I will explain this. So then there is again an open subset of Y. And
Владимирович, а это напоминание прошлого семестра или здесь что-то новое есть?
Well, I didn't explain this last semester. Maybe if you solved all the exercises, you know this, but maybe not everybody solved all the exercises. Yeah, but at least it was not in the lecture. But if everybody knows this, well, just tell me and I will skip this and go to the next topic. So I don't know. Let's take a vote or what? Shall I skip this? Well, if there is no opinion,
Просто могут быть люди, которые смотрят записи.
all right, yeah, and who cannot vote. So I'd rather continue. Yeah. Okay. Thank you. Yeah. So there is decomposition of this F into the following. So I have the pre-image of U. Then it goes into U times some affine space, and then it just projects onto U. So this is our F. And in this decomposition, G is a finite surjective morphism. Okay. So now, if we assume this lemma, so modulo the lemma, the proposition is immediate. So first of all, we know that G and projection are both surjective. Hence, U is the full pre-image of its image, and the dimension of any fiber is the dimension of its fiber under projection, because just a moment. Sorry. So the dimension of this fiber is the same as dimension of the fiber of projection, because G was finite surjective, and it does not add anything to the dimension of fiber being finite, right? And this is clearly n, and it is constant over U. Okay, and finally, the dimension of X is the dimension of the pre-image of U, because it was open. So it is dimension of U plus n, and there we are. So the proposition is proved, modular lemma, and we only have to prove this lemma. So let's do this on the next page. So essentially a minuter that I proved half a year ago. So let's consider the induced map of functions. So functions on y into functions on x, and now let's localize. So this embeds into the field of rational functions on y, and here it embeds into the extension of scalars. Okay, and let's maybe denote this by A. So it's and it's an algebra, and this algebra is a finitely generated module over the field of rational functions, and just similarly to the proof of a Minotaur lemma. There is a subalgebra K of Y over some free variables, like this. It's polynomial algebra inside of A, such that A is a finite type. Maybe let's call it B. B module. Okay, and since it's a finite type B module, then any element of A satisfies some equation with the leading coefficient 1. So let say Y 1 and so on, Y capital N be generators of this algebra A, and each of them satisfies an equation like Fi of Y J of Yi equals Yi to the power Di plus I1 Yi to the power Di minus 1 plus so on plus Ai Di equals 0. So these A I whatever K lie in this algebra A, and the A was, as you remember, functions on X, tensor rational functions on Y, but there are finitely many of those coefficients. Of those coefficients altogether, finitely many of Yi's and finitely many for each of them, and they are rational functions, so they have some denominators, but there are finitely many denominators altogether.
Извините, а под знаком тензорного умножения не нужно случайно f со звездочкой k, y написать?
Well, it's up to you. You may.
Это будет правильно или неправильно?
It's up to you. I don't know. It's a module over functions on Y, but this model structure is indeed via F. So you can say it's via F upper star if you want.
Спасибо.
Okay. So there are finitely many denominators, and let A be a common denominator. Okay, and then you see that all those coefficients lie, so any a I k lies in the localization of this thing localized with respect to a, and maybe I should say how to say maybe k. Oops, but by the way, I said something wrong. So these coefficients, these coefficients, they were not in the ring A itself, but in B, right? So in polynomials. Sorry. So these coefficients lie in B. Okay. So it was k of sorry. And here I must say the same thing. Okay, and now we are done. So we just take this open subset U. It's just the
Что такое маленькая вот KY?
the common denominator of all these coefficients.
Спасибо.
Okay, so they were polynomials with coefficients in rational functions on y. So these rational functions might have some denominators, and now we could take the product of all these denominators, the common denominator. Okay, and we only have to invert this one. Everything else is regular on y. Okay, so if we just throw away the zeros of a, then on the complement, this is a regular function, and this complement is our desired open set U. Okay. So there we are. And now we can deduce the desired Chevalier theorem. That the image f of x is constructible. So this means it's a finite union of locally closed subvarieties. Okay. And this is just by Noetherian induction. So we start with U as in the proposition. And then U is open in the closure of the image of X. So U is locally closed in Y. That's fine. But now we see that the image of X is this open set U. Sorry, how shall I say? This open set U, and also the image of the boundary of X, so to say. Okay. No, maybe I should write just U like this. So the open set, and the disjoint union with the image of the boundary. But because we know this dimension estimate, the boundary has smaller dimension. Smaller dimension. So we can proceed by induction. Okay, there we are, and it's a very useful theorem, and also what is nice, it was proved by Chevalier in the middle of 50s, so after the Second World War, and maybe this is one of the first results in algebraic geometry that we learned that was proved after the Second World War. And now another corollary that's also very useful. And if somebody goes to the class by Jgun about algebraic groups, then he must know this. And does anybody go to this class? No? Nobody? You do? Okay. So if we have a homomorphism of algebraic groups, be a homomorphism of algebraic groups, then its image f of h in G is a closed subgroup. And you see, in the usual differential geometry, in the theory of Lie groups, this is not true, right? Because you know that it's wrong for say real Lie groups.
Собственное отображение, ну то есть
No,
FH может совпадать с G.
Well, it can be equal to G, yeah, but it's not very interesting case. But so you know that you may have a torus like this, and then you can so it's two-dimensional real Lie group, yeah, and then you can have one-dimensional, one parametric subgroup that goes around like this and goes and goes and goes and goes, and it's dense. The image of this subgroup is dense in the ambient two-dimensional torus. But for algebraic groups and algebraic morphisms, it never happens. So the algebraic geometry is much safer place to live than just real differential geometry.
Sorry,
yes.
Can I confirm that? Is it true if H is locally compact and Hausdorff space in general case? General case.
No, I mean, so it's what I try to draw here is a homomorphism from R into the torus, well, S1 squared.
Okay.
So certainly R is Hausdorff and locally compact and whatever you may wish. A very nice space. Okay. So let's prove this. And what do we know? We know that the image certainly is a subgroup, and it contains an open and dense subset U inside its closure. Okay, just by the proposition we proved before. And now you know that certainly H is invariant by the shifts by this U, because U is contained in f of H. So since f of H is invariant with respect to shifts by U, you know that f of H, oops, sorry, wrong. Let me go. F of H is open in its closure. Okay, just because U is open, and for any other point you can just shift this point into U, and so any other point also contains a neighborhood inside the closure of f of H. Okay. Now again, any shift of this is also open. So for any G in the closure, the shift G times f of H is also open, and hence the intersection G times f of H with f of H is non-empty, because these are two open subsets, and hence G can be written as an inverse, well, as a ratio of two elements here. But this ratio is nothing but an element of the image. Okay, and hence, well, so you see, G lies in f of H, so f of H is closed. Okay, we proved this theorem. That's fine. And now another important result, which was in the exercises and was used in the exercises, about semi-continuity of the dimension of fibers. So again, we have a morphism, and then the function x goes to the local dimension at x of the fiber through this point. Okay, so this function from capital X to positive integers is upper semi-continuous. So it can only jump under specialization. Yeah, if the point X is generic, then I have certain dimension of fibers, but then if X specializes, then this dimension of fiber can jump, but cannot drop. And moreover, if X is irreducible, then each component of this fiber has a dimension, at least the relative dimension, x minus the dimension of the image.
So does it mean that
Yes.
for some major zero sets, it's improved the dimension, like it's going up with dimension for major zero sets?
Sorry, I missed your question. Can you repeat it, please?
Yeah, for major zero sets, it
Yeah.
means that it's going up dimension.
Yes.
Okay,
Yes.
okay, I see.
Well, we do not really define any measure theory, but intuitively, yes.
Okay.
Generically, you have some dimension, but then on the boundary over measure zero complement, the dimension can jump.
Okay, yeah, makes sense.
Like in this blow up, yeah, in the blow up business, the dimension of generic fiber is 0. It's an isomorphism almost everywhere, but over the origin you have a big fiber in the projective space, right? So the generically dimension is 0, then it jumps to n. Okay. So maybe let's prove B first. So again, it's local. So may assume that y is the closure of image of x is affine. And then you take a point, let's say y is f of x, and there are functions on y, like g1 and so on, gd, where d is the dimension of y, such that this point y is a component, irreducible or connected component of the zero set g1 equals so on equals gd equals 0. Yeah, last year we had such a claim, and even more general. So we had an equidimensional subvariety of some equidimensional variety, maybe affine, and then we claimed that we can choose a number of functions on the ambient variety, and the number equals the codimension, such that the subvariety is just one component, or if it's not irreducible, then a few components of the zero set of those functions. Okay, we proved this sometime in October, I think, and now let's use it. Because it implies that any component of the fiber over this point has dimension at least the relative dimension. Okay, because in the base this point is cut out by d equations, at least locally, and the same equations cut out the fiber in the total space, right? But since you have d many equations, the dimension cannot drop more than by this d. Okay? that's what we wanted to prove for B. Now let's go to the first statement. A at the upper semi-continuity of the dimension of fibers, and again this will be proved by some sort of Noetherian induction. So to prove A, we may assume that X is irreducible. Yeah, we can just prove it for any reducible component and then take their union, and then take U as in the proposition above. So it's in Y, and then the dimension of fibers will be the difference of dimensions, the relative dimension for any X over U, just by this proposition, right? And hence this local dimension of the fiber is constant over U, and it's constant on the pre-image of this U, and we know that the dimensions, the local dimensions of the fibers everywhere else is at least well, maybe let's call this constant C, is at least this constant C, right? For any X, just by the first, just by B, I mean, by the second claim. Okay, so we have to check the first claim A for the boundary. Dx is X minus the pre-image of U, and we are done by the Noetherian induction. Okay. So this was what you proved or used in your home assignments the last semester, and now let's move on. Namely, let's consider the normalization procedure. So I will presently define it, but it's some, so to say, first approximation to resolution of singularities. It's a step towards a resolution of singularities. I mean, next time we'll start studying algebraic curves. So they are algebraic varieties of dimension 1, and in this sense, they are maybe the simplest algebraic varieties. But still, as you might remember from the previous semester, they might be pretty singular.
Владимирович, извините, я запутался, пропустил. А вот dx, что это такое вот обозначение, символ? Вот я...
The boundary.
Граница, конечно.
Yeah, the boundary. So we checked something on the interior over this open subset U in the base Y, but we know that in the boundary, in the complement to this interior, the dimensions of fibers can only jump, and then we proceed by induction. Okay, again, in the boundary we find some open subset in the boundary of Y, playing the same role and so on. Okay, so about normalization, we can consider singular curves like this or like that with big Zariski tangent spaces at the singular points, but then the normalization in all the cases will be a smooth curve which projects onto this singular one, and the projection is an isomorphism away from singularities. Normalization. Will be smooth and isomorphic to the original curve C away from its singularities. Unfortunately, it works literally so only for curves. So already for surfaces, you can have normal surfaces that are singular. For example, if you just take the most standard quadratic cone like this, it'll be already normal. So its normalization will be isomorphic to itself and will not resolve its singularities. Because to resolve its singularities, you need to blow up at the vertex of this cone, and after you blow up, you will introduce the exceptional divisor, which will be one-dimensional, just P1, smooth conic at this point. But the fibers of normalization are always zero-dimensional. And in fact, this normalization, pi is a finite morphism. Finite morphism always.
Sorry, normal variety is variety for which all local rings are normal, yeah?
Right. I didn't give a definition yet, but I will momentarily. So the definition is that Y is normal if all the local rings O, Y are integrally closed in the field of fractions. Sorry. Well, okay, so it's a local property, so you may assume that Y is affine if Y is affine then the ring of functions must be integrally closed in the field of rational functions. Okay, and now I gave a definition of a normal variety, but I didn't say yet what is normalization. Normalization is some canonical, well, universal procedure that replaces an arbitrary variety by a normal one. And I will define it in some more general setting. So namely, let me take an irreducible variety, y be an irreducible variety, and we'll have a field, say K, a field of rational functions. And L will be some finite extension. Sorry. So it's another field, and then we will define a normalization, well, the normalization of this variety in this field. Of y and L, and in particular, if L is a trivial extension, just K itself, then, well, this procedure is called the normalization y of y. And in general, it will always project onto y, but it will be not an isomorphism over the generic point. But in case L equals K, this normalization will be an isomorphism generically. Okay, so how do we define this? Well, now I'm too late. So maybe let me still define it, and then next time we will prove the basic property, say the normality property. So we define. Well, let's go to the next page. Define a coherent sheaf of algebras say A over the structure sheaf of Y, and we set this normalization in the field L, in the field extension L, is just the relative spectrum of this sheaf of algebras. If you remember, we had such a problem set sometime in November. Yeah, explaining that the affine morphisms are the same as the sheaves of algebras over the structure sheaves, or over the structure sheaf. Okay, and this is an example of application of this construction. Okay, so how do we define this coherent sheaf of algebras? We take a quasi-coherent sheaf L tilde over Y. Okay, maybe, well, I don't know if you remember how we dealt with coherent, quasi-coherent sheaves, but this was some fancy example. Yeah, this is a sheaf that is actually a constant sheaf, but also a quasi-coherent. So all its sections are the same field extension. So L of any open set is just the same L, and maybe here with well, for a fine U, let me say. Okay, because I mean, then it makes sense to take localization. So this is just localization. Okay, and certainly we have the structure sheaf embedded into this big quasi-coherent constant sheaf, and inside we have the this field K tilde that was just the rational functions on Y, like this, and finally we define the desired coherent sheaf of algebras as its sections over U is the intersection of all points in U, the integral closure of the local rings in the field L. Okay, so we wanted all our local rings to be integrally closed, and we did this just by decree, right? We just declared that these are our local rings, and globally we just took the intersection of all these local rings, and then next time I will prove that this gives something coherent and even finite, and this will be the desired normalization in L. So that's it for today. So sorry for being late. And are there any questions? If not, let me save the lecture notes and stop the recording.